Welcome to the 16th lecture in general topology. The topics that we'll cover in this lecture include measurable spaces, Borel sets, measure spaces, and in particular we will look at two very important measures, the Borel measure and the Lebesgue measure. Okay, so in this lecture we're going to explore some of the very basics of measure theory. Measure theory has lots of applications, in particular in analysis, complex analysis, and integration theory. For us, we're going to be interested in two specific types of measures, the Borel measure and the Lebesgue measure, which will allow us to more easily present topological dimension when we get to dimension theory. And also, the idea of a measure is very similar to the idea of a metric on a given space. So without further ado, let's get started. A collection of subsets which we give the symbol script M of a set X is called a sigma algebra in the set X if the collection script M has the following three properties. Sigma algebra. 1. The collection script M must contain the entire set. 2. If a given set is in the collection script M, then the complement of that set is in the collection. 3. If we have a countable number of sets in the, or a countable family of sets in the collection script M, then the countable union of those sets is in the collection script M. All right? So if the collection script M is a sigma algebra, in the set X, then the collection of the set together with the sigma algebra is called a measurable space. Notice the able in the measurable. We will soon look at what is known as a measure space, but that requires a specific measure to find on the space, in addition to what we have here, a measure, a function. We'll get to that. So the collection script M together with the sigma algebra defined on the set together with the set is called a measurable space. And the members of the collection script M of the sigma algebra are called the measurable sets of the set X. All right, so two things to point out immediately. The prefix sigma in sigma algebra is from the French word sum, which means union, and it refers to the fact that all countable unions of measurable sets must be measurable. So we can restate the three properties. Of the sigma algebra. In terms of the measurable space. The first is that the entire set must be measurable. Two, if the set A is a measurable set, then its complement is measurable. And third, countable unions of measurable sets are measurable. Okay, so we come to our first theorem in measure theory. Let X, together with some sigma algebra defined on it, be a measurable space. Then the empty set is measurable. 2, if we have a countable collection of sets. Then the countable intersection of those sets is measurable. Third, if we have two sets, A and B, that are in the sigma algebra, then the complement of A and B, which we generally call the symmetric difference, is in the sigma algebra. All right, so the first statement is very easy to prove. Since the entire set is measurable and complements must be measurable, the complement of the entire set X is the empty set, and so it is measurable. 2, let this countable collection of sets be in the sigma algebra. Then the complement of these sets is in the sigma algebra. And so we have that the countable union of these complements is in the sigma algebra. Now, since the countable intersection of the sets A sub n is the complement of the countable union of complements, we see that the countable intersection of the sets A sub n is in the sigma algebra. All right, third statement follows directly from the second. Let the sets A and B be measurable sets. And since the symmetric difference is the intersection of the set A with the complement of B in the larger set X, and countable intersections of measurable sets are measurable. we see that the symmetric difference, or the complement of B and A, is measurable. Right? So those of you who have taken courses in algebra or are true algebraists may have noticed that the definition I gave for sigma algebra said nothing about an algebraic structure. Instead, the definition was given in terms of sets. So it was a topological definition. So we'll quickly discuss the algebraic structure for sigma algebra. The algebraic structure is a set consisting of that collection of subsets that we call the sigma algebra that is closed under countable unions, countable intersections, and complements, whether that complement be within the a true complement in the large set X or symmetric difference. Now notice that if we know the sigma algebra, we know the underlying set. It's simply the largest set in the sigma algebra, because the sigma algebra must contain the entire set. All right? So now we'll define what we mean by a measurable function. If the space X is a measurable space, and the space Y is a topological space, and we have a function f mapping the space X, the measurable space X, into the topological space Y, then the function is called measurable, if and only if for every open set V in the topological space Y, the inverse image of that set is in the sigma algebra, or is a measurable set in X. Okay? So now a new theorem. Let X be a measurable space, and let Y and Z be topological spaces. If the function f mapping X into the space Y is measurable, and the function g mapping the space Y into the space Z is continuous, then the composition f with g is a map from the measurable space X into the topological space Z, and this composition is measurable. Okay, so now we prove the theorem. Let the set V be open in the space Z, and let H, we'll just rename the composition, we'll call the composition G of F simply H. So as the set V is open in Z, the inverse image under the map G of the open set V is open in the space Y, as the function G is continuous. And so the inverse image under the map F of the inverse image of the open set V under the map G is a measurable set. In the measurable space X, as the function f is measurable. And so we have that for every open set V in the topological space Z, the inverse image under the map H of that open set, which is the inverse image under F of the inverse image under G of the open set V, is a measurable set. In the measurable space X. And so H, which is our composition, is measurable. Okay, so this is a very useful theorem. It tells us that if we have a measurable function from a measurable space into a given topological space, then any continuous function from that topological space into a second will produce a measurable function under composition. And as I stated before, most of the applications are in real and complex analysis, and so many of the theorems will present that composition with a with the topological space being either the real line or finite dimensional real space as kind of a starting or launch pad into other topological spaces. And so the next theorem is one such theorem. Let U and V be real measurable functions in the space X. Let the space Y be a topological space. And let the map phi be a map from the real plane into the topological space Y. And let this map be continuous. Then the function h, which is going to be a map from the measurable space X into the topological space Y, defined by h of x is phi, taking as an argument u of x and v of x. So our measurable functions on x are the arguments for the function phi. Then this map is measurable. Okay, so notice that we're the continuous function that I mentioned happens to be from a finite dimensional real space into some second topological space Y. All right. Okay, so need to make a few remarks before we proceed with the proof. The functions u and v are real measurable functions in x. That means that u is a function from x into the real line, as is v, a map from x into the real line, where the assumed or implied topology is the standard topology. And the same is true for the function phi from the real plane into the space y. This is the standard topology on the reals. Okay, so we can now proceed with the proof. We're going to define a function f from the real line into the real plane, and we'll let f be defined by f of x is the ordered pair u of x v of x. So the function h is now the composition of phi with f. So by the previous theorem, the function h is measurable if the function f is measurable. So we need only prove that the function f, as defined, is measurable. So let the set V be open in the real plane. Then V is the product of two open sets, u sub 1 and u sub 2. And u sub 1 and u sub 2 are open in the real line. So the inverse image under the map U of the set u sub 1 is a measurable set. Now, and the inverse image under the map V of the set u sub 2, these are both measurable sets. In X. And so the inverse image under the map F of the set V is the inverse image of the product of u sub 1 with u sub 2, where again these are open sets in R. And this is the intersection of the inverse image under the map U of the set u sub 1 with the inverse image under the map V of the set u sub 2. So this is a countable intersection of measurable sets. And so is measurable. And again, by the previous theorem, as f is measurable, the function h, which is the composition of phi and f, so phi of f is measurable.